purpose of this video is to go through the rotational inertia of a pulley system with a single suspended mass. Okay, we'll start out with our problem with some reasonable numbers here. So 50 gram mass, M1, is suspended from a lightweight string. The string is wrapped around a 1 kilogram disc pulley with rotational inertia as given. The system is initially at rest, but then it's allowed to accelerate. The string does not slip around the pulley. The radius of the pulley is 15 centimeters. And we are going to determine the angular acceleration, alpha, of the pulley, tension in the string, T, and the linear acceleration of the mass, M1, alpha, A. So I've drawn a picture of the system and included all the given variables. So if we're looking at a system that is not only has rotational motion but also has linear acceleration, we're going to employ Newton's law in both a rotational sense as well as the linear sense. So if we look at what's going on in the linear, we have the sum of the forces is equal to mass times acceleration, and the rotational analog is going to be the sum of the torques is equal to the rotational inertia times alpha. This applies to the mass M1, while this equation is going to apply just to the pulley. Now the thing that links these two equations together is what we call the non-slip condition. And that's kind of in the wording, and it may seem a bit extraneous when we're reading about the fact that the string does not slip around the pulley, but it enables us to say that if I look at a point just tangent to the edge of the pulley, that tangential acceleration of that piece of rope right there is related to the rotational acceleration of the disc through this equation right there. So we can connect the two things together with the non-slip condition. So let's go ahead and start writing out our net force equations for both rotational and linear systems. So if we focus on M1 as my system, we know that the weight of the mass, M1 times G, minus that tension force is going to be equal to the mass of my system, which is just M1 times A. Immediately you can see, and just as a reminder, that the tension has to be less than the weight of the block. Otherwise this thing is not going to accelerate or move. So we're saying that the mass is going to accelerate down, so T must be less than M1 times G. So solving for my tension force here, I can get tension is equal to M1G minus M1A. So I have an equation for tension. Now I go over to the rotational side of the equation. This one's maybe a little bit more complicated, but if we look at our system and ask what is the force that's providing the torque, well, the string itself is touching the disc at a distance r away from the axis of rotation. So it's the tension in the string that's providing the torque. So I'm going to use capital letter T times the radius of the pulley, that's going to be our torque, times the rotational inertia of my system, which I'm going to go ahead and plug in as md r squared, times alpha. Now I could leave this just as I and maybe substitute it in later, but you might see that some things cancel out and make it a little bit more simple of an equation. So I have this equation here, I have my linear equation, and then I have my non-slip condition. I have three variables and three unknowns. I don't know the tension, I don't know the angular acceleration, and I don't know, what else don't I know? Tension and linear acceleration. So those are the things that I want to solve for. So you have a little different ways. You don't have to solve the problem in the order that it's given, but I might as well just start there. It does not really matter which order you start solving in it. So if I want to solve for the linear acceleration, I can get rid of the, if I want to solve for the tangential acceleration, I can get rid of the linear acceleration by using the non-slip condition. So if I substitute in that A equals R times alpha, then I get an equation for tension M1G minus M1 R times alpha. And then this equation over here, I can solve it for tension. It's just 1/2 mass of the disk R squared alpha divide by R. You can see that one of the R's cancel out, and I'm left with a tension equation that is 1/2 mass of the disk R alpha. So I can set these two equations equal to each other. M1G minus M1 R alpha is equal to 1/2 mass of the disk R alpha. If I'm solving for my angular acceleration, I can isolate that variable. So I get M1G is equal to 1/2 mass of the disk R alpha plus M1 R alpha, like that. Factor it out. And finally, I can just solve for alpha. And an equation alpha is equal to m1g over 1/2 mass of the disk r plus m1r. So there you go. So there is an equation right there that I can just substitute the numbers in and begin to solve for my answer. So I'm going to go ahead and do that. I'll pull it down here so I can still see my equation. Okay, so alpha equals m1 is going to be 50 grams, which we know is 0.05 kilograms. I'm going to use 9.8 because I'm a purist. 1/2 mass of the disk is 1 kilogram. Radius is going to be 0.15 centimeters, which I realize I wrote down incorrectly in the beginning, so I had an extra 0 in there. You can ignore that. Plus M1, which is my 50 grams, which is 0.05 kilograms. I didn't mess up my decimal there. And then the radius, again, 0.15 meters. So if I plug all that in, and I've done my math ahead of time, and hopefully you'll forgive me if I messed up with my calculator, I ended up with 5.94 radians per second squared for alpha. Okay. Now, moving along, I can solve for tension, and it doesn't really matter if I use the equation that I had for linear acceleration or rotational acceleration, or I'm sorry, my tension that I developed through the linear version of Newton's law, or I use the equation for tension from the rotational version of Newton's law. I can use either one. So these were the equations that I had developed on the previous page. M1 minus M1R alpha. That was for the linear, and then the other version was 1/2 MDR alpha. It doesn't really matter which one I've used because I've solved for alpha already, so I'm just going to pick this one. No real reason behind that. 1/2 mass of my disk is 1 kilogram. Radius of the disk is 0.15 centimeters. And then alpha we just solved for was 5.94 radians per second squared. So substituting all those in, plugging it through, forgive me if my math is incorrect, but I think it's alright. I ended up with 0.45 newtons. And then finally, the last part was determining what the linear acceleration is. And probably the easiest thing to do is just, since we have the non-slip condition, is just take our value for the rotational acceleration and multiply it by the radius. So that is going to be r, which is 0.15 centimeters, times 5.94 radians per second squared, and I believe my answer is 0.89 meters per second squared. So hopefully that clears up any kind of confusion that you had with setting up these equations and being able to solve for it. Once you write Newton's laws for rotational and linear, the rest of it just becomes an algebra problem, and you end up with 3 equations, 3 unknowns. Remember the non-slip condition, and you should be fine. Okay, good luck.